So the first sample problem we have is how many times greater is the surface gravity of Jupiter than Earth? So let's write down what we know. Well, at first glance it appears we don't know much. We always know Newton's universal gravitational constant, 6.673 times 10 to the negative 11th Newtons meter squared per kilogram squared. But we're not really given anything in the problem. However, it's pretty easy to look up mass of the Earth and mass of Jupiter. So we'll go ahead and look those up so that we have those numbers to work with. The mass of Earth is 5.97 times 10 to the 24th kilograms. So 5.97 times 10 to the 24th kilograms. The mass of Jupiter, 1.89 times 10 to the 27th kilograms. So now that's something to work with. What we're solving for in this problem is g, the surface gravity, okay, our lowercase g. Equations. Well, we have Newton's universal gravitation. The force of gravity equals g m1 m2 over r squared. We also have that force of gravity normally when we're on the surface of anything is mg. That's normally how we would calculate, say, weight, for example. Well, since both of these things are equal to Fg, let's go ahead and in our plan say that we're going to set those equal to each other. So set Fg's equal, and then just simply solve for our lowercase g for each planet. So the solution, right, we're going to set those equal to each other. So mg equals g m1 m2 over r squared. Masses cancel out, and then so we have g equals capital G m squared over r squared, or m2 over r squared. So m2 here is going to be the mass of the planet. R squared should be the radius of the planet, which we forgot to write up here in our known values, but again is just something that we could look up. So g for Earth, well, let's just skip ahead a little bit. We know that should come out to 9.8 meters per second squared because we're used to using it. So let's just really worry about Jupiter. So Jupiter, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And the mass of Jupiter, 1.89 times 10 to the 27th kilograms, divided by its radius, which if we look that up is approximately 70 million meters squared. If we plug that all into our calculator, we get 25.7 meters per second squared. So a much greater gravity than Earth. If we divide those two, so 25.7 divided by 9.8, that gives me about 2.6 times greater than on Earth. So for the second problem, we want to know how fast does a satellite orbiting 5,000 kilometers above Earth move in its orbit? So what sort of things do I know? Well, I know sort of a radius of 5,000 kilometers, but that's not quite right. See, when we're doing any of these Newton's universal gravitation laws, it's not just, so there's the Earth, there's the satellite, so this distance would be the 5,000 kilometers. It's actually the distance we want is from the center of the Earth to where the satellite is. It's the difference. It's the center of masses is really what we're interested in. So what I have to do is for my radius take 5,000 kilometers, which is 5 million meters, plus the radius of the Earth for my actual orbital radius. So that is 6,371,000 for Earth plus the 5 million for the satellite, and I get 11,371,000 11,371,000 meters for my known radius. And that's really the only piece of information I have. I might need to look up a mass of the Earth since we're talking about things in orbit. And that is 5.97 times 10 to the 24th kilograms. What am I solving for? I'm solving for a speed. I'm solving for a velocity. Okay, velocity equals. So the question is, how do I get that velocity and force together? Well, I know the force that's causing it is gravity, so I can use Newton's universal gravitation. But what is it causing? Well, it's causing an orbit or a circular motion. So in this case, our force of gravity is going to be a centripetal force because it's causing something to move in a circular path. So that's equal to mv squared over r. So my plan here is that I'm going to set centripetal force and force of gravity equal to each other because force of gravity is my centripetal force in this case. And then solve for the velocity. So my solution looks something like this. I'll have mv squared over r equals g m1 m2 over r squared. What happens is the mass of the satellite is going to cancel out of the equation. One of my radii over here is going to cancel out, and then this one is going to cancel out completely, so that I get v squared equals g m2, which in this case is mass of the Earth, mass of the object being orbited, and then square root both sides. So v is going to equal the square root of g, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times my mass of what I'm orbiting, the Earth, 5.97 times 10 to the 24th kilograms, divided by my radius, which is that total distance between the two, of 11,371,000 meters. So I get a velocity of 5,918 meters per second. And that's how fast that satellite would be moving if the force of gravity was the only thing causing its motion.